Hi, my name is Tan Heng Jun, and here is my submission for the EM3 assignment on Euler's method. Let's start with the Euler's method and what it is. It is named after Leonhard Euler and is a numerical technique for approximating solutions to ordinary differential equations. The technique is based on the idea that the value of a function at a point can be approximated using line segments. The idea is that the derivative of a function can estimate how much change there is in y for each change of x. Let's suppose a function f of xy. We'll be using the gradient of the derivative to approximate the y values, which I did here. To approximate the y values using gradient, we will use the formula rise over run. So we take yn plus 1 minus yn divided by xn plus 1 over xn. Xn plus 1 minus xn. Xn plus 1 minus xn can be simplified to step size h, which is simply the interval or difference between them. Simplifying this to h and bringing it over, we get h multiplied by f prime of xy equals to yn plus 1 minus yn, which we can then further simplify by bringing yn over to yn plus 1 equals to this formula, which we'll be using later. Here is the example question. For dy over dx equals to x squared plus 1 over y, where y is more than equals to 0, and given the initial value, find the appropriate value of y1. We can bring dx over and y over to get y dy equals to x squared plus 1 dx. We can then integrate both sides to get y squared over 2 equals to x cubed over 3 plus x plus c. Given the initial condition of y0 equals to 1, we can find c equals to half. Substituting c equals to half and the initial condition back into the formula, we can find that y, the value of y at 1, is equals to square root 11 over 3, which is roughly 1.915. And this should be the exact answer. Now let's cross-check against Euler's method to see how accurate it is. So using the step size 0.1 and subbing in this x equals to 0 and y0 equals to 1 into the formula, we can get 1. The new y value y1 is y0, the previous y, plus this product 1, product with 0.1, which gives me 1.1. We can then repeat these steps to get the next y value, which is 1.918, which we can cross-check to our Excel sheet later. Here's my Excel sheet. I did two Euler's method, one for 0.1 and one for 0.2, so we can compare the accuracy later. Let's start with this. The formula for y is given by the previous y value multiplied by the function of y product with the step size. The function, the formula used for this function is given by x squared plus 1 over y. And it's the same for all going down. Okay, it's the same for this as well. Now let's look at this. This is the values I plot for 0 to 1 for the exact values that we have found earlier in the general solution to see how accurate it is. We can see here that both are very close to each other. 0.1 almost overlaps with the exact values. But here in 0.2, there is a slight bit popping out. So from this, we can tell that 0.2 step size is less accurate than 0.1, which is also reflected in this error approximate. Thus, we can conclude that the smaller the step size, the more accurate it is. Thank you.